Anyway, as promised, no more new rules. Just lots of word problems. There was such so the rest of chapter 3, so basically today and Thursday, and then pretty much all of chapter 4 is using the rules of differentiation to find things. And why did we now know all those rules? So the first one we're going to look at is actually one that you guys actually do every single day when you drive. So when you're driving in your car, we don't typically think about it this way, but your speed is actually a derivative. So the miles per hour in your car, that's a derivative because it's a slope. It's miles per hour. So by definition, that makes it a derivative of where you physically are. So your position is actually the equation. Your velocity or your speed would be the derivative of your position. And then your acceleration is actually the derivative of that. So the second derivative. A lot of times you only end up seeing the velocity, so that speed. And actually what we're going to look at the end of chapter 4 is how to go backwards. Where we're going to have, okay, if we know our speed, where are we? Or if we know our acceleration, how fast are we going? Those types of things. We'll be able to go backwards using integration. So the position of a particle is given by this equation. We want to find the velocity at time t. So all you're going to do that, take the derivative. So take the derivative of that function there. So whenever you see s, that's considered the position of the particle. In this case, we're looking for the velocity of t, which is the derivative of f of t. All right, so what's the derivative of f of t? Yep. So in this case, my velocity is going to be in meters per second. So my velocity is in meters per second, where my position would be just meters. All right. So what's the velocity after 2 seconds, or technically at 2 seconds? How would we do that? Let's plug in 2. So what's the velocity after 2 seconds? What was it? -8? Or -3? Oh, I didn't do it. So we got 12 minus 24 plus 9. So -12 plus 9 is -3. Yeah. All right. What's it after 4 seconds? No. Not 9. Oh, wait. I take that back. It is 9. I'm doing basic math horribly wrong. I did the 48 first, then I did 12 times 3. All right. So we had a theorem that we had talked about. What is something that happens between 2 seconds and 4 seconds? Okay, the velocity increases. What else happens between 2 seconds and 4 seconds? Huh? We go from a negative to a positive. Correct. Remember the intermediate value theorem? If we're going from negative to positive, at some point it's got to cross, since this is a continuous function, it's got to cross through all those values. So at some point between 2 and 4, it's got to be 0. Okay? That's actually important because the next question is, when is the particle at rest? If it's at rest, that means my velocity would be what? 0. So we're looking for the values that are going to give me 0. So I'm looking at 0 equals 3t squared minus 12t plus 9. So factor that and find me the 2 points where, or the 2 points where it's 0. For all those that didn't remember to factor out the 3, your problem became a lot more complicated. Always look for something you can pull out before you do it. So the 2 points where the particle is at rest, this time equals 3 seconds and 1 second. So when's the particle moving forward? How would we figure this out? All right, so let's go back to question B. What's the velocity in 2 seconds? All right, what does that mean? we're driving a car and we had a negative velocity, what would that mean? Huh? So what would a car be doing if I had a negative velocity? Oh, yeah, it'll go in reverse, right? We're going backwards. So here's an interesting thing. Anybody ever work on old cars? Normally I have something. So back old cars, like pre-1960. The speedometer, and well, not the speedometer, the odometer, where it actually tracks your mileage. If you drove backwards, it would run backwards. So you could literally take miles off your car by driving backwards. Or if you drove backwards all the time, you would literally put no mileage on your car. Then they figured out this is how people were actually running back their miles on the engines. They would literally put it up on a roller and just literally do it in reverse to roll back the engine's mileage. So they actually put a stop in the odometer. So the odometer wouldn't run backwards, but it just wouldn't go forward if you're going in reverse. Now that we have digital odometers and everything else, if you're going backwards, the odometer still will go up because it's tracking how many miles you've gone, not which direction you've gone. So a negative velocity would mean you're technically going in the opposite direction. A positive velocity would mean you're going forward. So the question says, when is the particle moving forward? So we're looking for when it has a positive direction. So how do we determine that? How can we determine when my velocity is positive? Yeah. Well, if we plug in t as 1 and t as 3, we're going to get 0, right? So we got to plug in ones that are around it, right? Okay. So if we just set up a quick little number line, and we put the 1 and the 3, let's do t equals 2 and t equals 4, since I already know those. And we'll do t equals, well, don't do 0. And actually, we could do 0. So if I t equals 2, that's negative, right? Because we already did that one. And t equals 4, that's positive. So t equals 0 is what? If you plugged in 0, what we get? We get positive 9. So it's positive. So over which intervals is the particle moving forward? From what time to what time? Yeah. Yep. From 0 to 1. And then 3 to infinity. So the particle is doing something that looks like this. That's what the particle is doing. All right. So the next question What's the total distance that this particle traveled in 5 seconds? How would we figure that out? What are we plugging in? Where are we plugging it in? Going back to the car, we're not figuring out the odometer. Okay. Where am I plugging the 5 in? For which t? My velocity or my position? Because right now we have 2 equations, right? And which equation? Okay, so the position, right? All right. So if we plug in 5 to that, what do we get? It's 125 minus 150. Can't do this off the top of my head. For 125. Oh, yeah, minus 150 plus 45. Yep, 20. All right, so we get 20. So it went 20 meters. Everybody agree with that? What's that represent? That represents how far away from it started, right? But what did this particle do at one point during its travel? It reversed, right? If it reversed, it still went that distance, correct? So we've got to count that. So so when we're looking at this, we actually have to look at how far it went from 0 to 1, how far it went from 1 to 3, and how far it went from 3 to 5. Because those are all distances that it went. So if we plug in 0 to S, we get 0. If we plug in 1 to S, we get 4. So how far is that line right there? That's 4 units, or in this case, 4 meters. Okay. Now, if we plug in 3, the next place it changes direction, we also get 0. So this one back here is going to be what? That's also going to be 4 meters. And we know when t equals 5, the S is 20. So that means this length right here is 20 meters. So how far did the particle travel in 5 seconds? 28 meters. We have to add all those together. And the old stock car where it stopped, it would have actually had 24 meters on the odometer because it wouldn't have counted the 4 that went back. But we need to count those 4. Because if you're walking, you still have those steps. Even if you walk backwards, your Fitbit still counts. Want to get a lot of steps? Put it on your cap. All right. Does that make sense? Because that's the thing. These problems, you're going to see a bunch of different ways that they're going to ask these questions in ALEKS and in your other classes. So like if you're in a physics class, this stuff will come up in physics. This stuff will come up in your mechanical engineering classes, your electrical engineering classes. Maybe not velocity and acceleration of those classes, but you're going to have other things that are going to be very similar to this respect. Anytime you're looking for a rate of change or instantaneous change, it's a derivative. So even if the class isn't teaching you it as that derivative, you can still, you know the calculus now, you could use the derivative to find it. And it might make your life a lot easier to get that answer than going through this big formula that you might have you do. That's the difference between your algebra-based physics and your calculus-based physics. Calculus-based physics is actually easier than the 2 classes because you use the rules to make your life simpler. For an algebra, you have to use the manipulation of the algebra to get the answer for you. So, but you need to know the calculus to be able to do it. All right. What's the acceleration after 4 seconds? So, hold on, I got to write my velocity equation back. So there's the velocity. So what's acceleration going to be now? That would be the rate of change of what? Of the velocity. So it's how fast your speed is changing. So velocity is how fast your position is changing. Acceleration is how fast your velocity is changing. Okay, so in this case, that means I got to take the what? My derivative of my velocity now. So A is typically used for acceleration. So that'll be 6t minus 12. So after 4 seconds, how fast is it going? Or how fast, what's the acceleration? And this is actually listed as meters per second squared. Because it's actually meters per second. So meters per second squared. Or miles per hour squared, depending on who you want to look at, depending on what you're doing. All right, so when is the particle speeding up? And when is it slowing down? What do I need to do to figure that out? So the particle speeding up when what is happening? We now have 3 separate equations. We have the position, we have the velocity, and the acceleration. So when the particle is speeding up, what's going to be true? Your velocity is increasing. Okay. And how do we... So if my velocity is increasing, that means what's going to be positive? My acceleration is going to be positive. And when it's slowing down, my acceleration is going to be what? It'll be decreasing. My velocity will be decreasing. So that means my acceleration is going to be negative. So if you literally just let off the gas in your car, your acceleration is decreasing. Your acceleration is negative. Your speed is dropping. Okay. So it says when a particle is speeding up or when it's slowing down, that means I need to look at my acceleration. What's going to be between those two places? So what's going to be between it speeding up and slowing down? It's got to be zero at some point, right? So if we can find that point, we can figure out which side is which. So let's figure out which side's which. So let's do 0 equals 6t minus 12. So at some point in here, that's where time equals 2. All right, so when is it speeding up? When is it slowing down? I just need to look at this and plug in a point in either side, figure out where it's positive and negative. So let's do t equals 0 and t equals 4. If I plug 0 into that, what do I get? Yep, so it's a negative. And if I plug 4 into that, I get positive 12. So it's positive. So when's the particle speeding up? Yeah. So 2 to infinity. And when's it slowing down? Yeah.
You never go to a negative number when you're making these intervals?
You wouldn't, because in this case, time can't be negative. So unless they specifically tell you that time is going to be negative, assume time cannot be negative. That's why I was kind of hesitant in plugging in 0 before, because technically that's where you were starting. So, and remember, we can't find derivatives or limits and stuff at an endpoint because we don't have anything that you're not going it from both directions. So it worked. It gave us the number we wanted, but technically you can't do that. So from when it's starting, it's decreasing all the way up to there. And then from there, then it starts increasing after that. Here's how your Alex problem is going to look. I'll make it bigger, don't worry. All right, so part 1 of the question. Particles moving along y-axis, position is y of t equals that, for when t is greater than or equal to 0. So it's again the time starting off at 0. V of t is going to be the velocity we want to find the position, the velocity, and the acceleration of a particle at t equals 6 seconds. So, step one for you is find me v of t and a of t. So find me the first derivative and then find the second. The one thing I will say, the vast majority of these problems are going to be relatively simple polynomials to do the derivatives of. They're not going to be overly complicated. Okay, you're not going to typically see square roots and rational functions and everything else. They're mostly going to be polynomials. Those should have been your two derivatives. All right, plug in 6 to them and find out the position, velocity, and the acceleration in 6 seconds. All right, what's my position? What's my positional value? Is that what everybody else got? Sound about right? All right, what's the velocity? I didn't do it, so I'm going to go off what you guys got. And acceleration. Was it 54? Those sound right? The confirmation from at least one of them. Good. Okay. All right. Where is the particle located at 6 seconds? At the origin, the left of the origin, or the right of the origin? To the left. Does it mean it's in the negative, right?
Yes.
Yeah, it's correct. It is using position. So using the y of 6. So it is to the left of the origin. In which direction is the particle traveling at t equals 6 seconds? So we're going to be using the what in this case. We're looking at how the direction it's traveling in. What would that be representative as? Yeah, that's going to be velocity. Because the velocity is positive, it's moving to the right, and if velocity is negative, it's moving to the left. Or thinking about a car, it's moving forward or moving backwards. So my velocity at 6 seconds is what? Is 108. So that means it's moving to the right. And then how's the speed of the particle changing? So if we're looking at how speed is changing, that's we're looking at the what? That's acceleration. So acceleration in this case is 54, right? So is it speeding up, slowing down, or not changing? It is speeding up. So it's speeding up. For the last two questions, if it was in neither direction, it's at rest or it's not changing, those would be zeros. For the first one, at the origin would be the 0. All right. I'll write the equation a little bigger if you can't see it. All right, find me my velocity and my acceleration. Yes. All right. The last part wants you to list the times when the velocity of the particle is decreasing at a rate of 9 units per second. So what does that mean? Yeah. Correct. So we're going to set the acceleration to -9. So A of t equals -9. So equals -30t plus 36. So I've got -45 equals -30t. So t equals 1.5. So for these questions, you just have to look at what it's asking. Everyone's going to be slightly different, but in the gist of it, that's the only things they're going to be asking you for is stuff to deal with velocity or acceleration. You just have to figure out which one goes where. And if they do what they do in the other classes, they will be mixed up. So it's not necessarily like the last one was in order. It is not necessarily always going to be in order. So definitely read what it says. All right. Next part. What is exponential growth? Okay. So that would be an exponential growth. So, but what does growth mean? By definition, is growth a position or a velocity? Why?
Because something new makes it might be bigger.
Okay, so growth means it's got to change, right?
Yeah.
So if you think about when you're a kid and you're growing, you're changing. You're not staying the same. Doesn't matter. You can be moving back and forth all you want. It makes no difference. It's a matter of how you're changing. So by that definition, exponential growth is a rate of change or decay, either direction. So exponential growth and exponential decay are a derivative. That's a derivative because it's a rate of change. So if we look at the actual definition of exponential growth and decay, which none of you have ever seen, although you've all done every problem that we're going to do on the board from this point forward on this, you've all done it. Because you've done exponential growth in algebra class, you've done it in pre-calculus class, you've probably done, you could have done it in stats and everything else. You've done exponential growth, you've done exponential decay. but you've done the algebra based of it where they've already given you the information. So growth is where it is a constant times its function. Okay, so it's some constant times its function. So which equation or which function do we know that ends up staying the same except for a constant when you take the derivative of it? What is the only thing that we've done that when you take the derivative of it, it stays the same except maybe for a constant? Yeah. E. Right? E to the x. The derivative of e to the x is e to the x. The derivative of e to the 2x is 2e to the x, because we do that. That's the constant. That's the only thing that could possibly change would be that constant. But e stays the same. That's why when you saw exponential growth, you saw it in an equation like this. Now, you might not have seen it with y to the 0 in there, but y to the 0 is just your initial condition. Okay? So that would be your starting value. If you've ever, well, we'll look at that in a minute, but like compounding interest and stuff like that follows along these same rules. So in K, that's your constant. That's the constant of change. That's the one we're going to have to calculate, given the information. All right, so we're going to use this equation. So the world population was 2,560 million, or 2.56 billion in 1950, and 3.04 million in 1960. So we want to use that to model the world's population in the second half of the 20th century. And then we'll figure out the relative growth rate in those things. So, first thing, what's P of 0? Right, it's 25,600. That's the starting point. So we're going to assume 1950 is 0. So when we're doing our calculations, we would use 1950 as that 0. Now, the next thing I got to figure out is what is K? That is my relative growth rate. Because that would be your K here. So how are we going to solve for K? So right now we have P of t equals 2560 e to the k t. So how can we find k? Okay. So we have the information for 1960, right? So what's going to be t in this case? Okay. And what's the population? 40. E to the 10. Okay. So we plug in the other information I have. As long as I only have one variable, I can solve it. All right. How do I solve it? What do I do first? Yep. So step one, divide, and I get 1.1875. All right, now go back to what we talked about last week. How do we get the variable outside of the exponent? What's the method we used last week to get variables out of exponents? I think I heard it earlier. I think I heard it a little bit ago. I just wasn't asking the question yet. Yeah. Yeah, we got to take a log of both sides. So since I'm using e, use the natural log. All right. And actually, I would use the natural log no matter what value was there. Although technically, if it was a different base, you could use a different log. All right, so I'm going to take the log of both, the ln of both sides. So the ln and the e is going to cancel out. I'm going to left with 10k. And then divide by 10. Now, I would suggest when you're typing this into Desmos, so I would totally suggest using Desmos for this. Don't actually like estimate as you're going through. Type the entire problem into it at one shot. So I did the ln of the 3040 divided by the 2560, and then I took 10, divided that whole thing by 10. So my k is that. All right. The next part of this question wanted me to figure out the population in 1993 and then 2025, amazingly. So 1993 is going to be what for T? This is where it's really easy to screw this up. It's not 93. It's 43. It's really easy to use the 93. And then for 2025, 75 and not 25. All right, so what is our population in 1993? This is where I like using Desmos, and I can just copy and paste that right up in there as just K. So I got 5360. Because then I can just type this in and do 75. And I get 9289. All right, what do you think the population of the world was in 1993? Think it was pretty close to that? That was the population in 1993. Now, we never count the people in the entire world. Unlike the United States, where we have a census every 10 years, which is kind of like mostly accurate, we never actually count the entire world population. Everything that we do is an estimation. It's based on a lot of calculations and everything else. So in 1993, they estimated it was 5.5635 billion, which is pretty close to what we had. And in 2024, which is the last one they have here, it's 8.142 million. So that's where we start to get a little further off in our estimation. Okay. But that's kind of the issue with, yeah. You could. A negative number in for T. So that would have been 1930. If I did 20 years, right? Yeah, it would be 1930. So 1930 was approximately 2 billion people. Pretty close. So, but again, anytime you get further away from those, it's going to vary a little bit more. Yeah.
Definitely will.
Let's see. No people. Right. So, but that's actually a really good thing to start looking at when we're looking at these, is that when you're looking at models, models work for where you have the data for and a little bit on the other side of that. Okay. But once you start getting further and further away from that starting point or where you have the data to use, it will start to get more and more unlikely. Like if we were to put 100 years, they're talking just over 14 billion people in 2050. It's not going to happen. But that was the fear for a while. That was the thing. Like, oh my God, we're going to be completely overpopulated. It's like that was the fear because people take the models and they run with them. And exponential growth is exponential growth. It's going to continue to grow like that. But in reality, it's not necessarily the same. Yeah. Honestly, the actual space-wise, we can sustain a crap ton of people in the world. There is tons of places to be able to house people. That's not the problem. The problem is feeding them. And that's why we're actually able to even sustain the population we are now, is we're getting better and better at growing food. We can produce food at a rate that is higher than we actually need right now. Like, I think the United States wastes like billions of tons of food every year. Like, it's the insane amount of food that we just waste. So, like, we're at the point where we can sustain a lot more than we would have, say, 30 or 40 years ago, because our technology has gotten better for that respect. Now, it's not to say that we want 40 billion people on the planet or whatever else. Like, we don't want that. But the other thing that happens in science is that our birth rates are going down. The United States is actually now under replacement value. We're less than 2 kids per family, which is what you need for replacement. You need 2 people to replace you. So we're under that now. So is Japan. Japan's way under. I think Japan was like at 1.3. So like that means that your population will start to shrink in those respects. Worldwide, we're not under that. There's places that are a lot higher than that. And that's why we're still seeing growth over 9 in the world. But that's the pieces where we start to use these models, like how do we actually use these to predict things? Which can only work so long. So, all right. This is the velocity of a skydiver that's crashing to Earth. So, anybody actually ever jump out of a plane? Okay. I have not either. My brother-in-law did. I have no desire to jump out of a plane. But as you fall, your velocity increases. Okay, that's the way gravity works. It's pulling you faster. Gravity is, in essence, your velocity is pulling you faster and faster. So as you fall, your velocity increases. So this is the velocity of the skydive. What's the velocity after 3 seconds? These are some of the topics in out. So now not everyone is going to have to do a ton of solving. Some of them are going to be very simple. What was the initial velocity? For the skydiver? Do we even have to? Which value in that formula is always going to give you the initial whatever? In this case, the initial velocity. You could plug in 0 for t. And if you plug in 0 for t, you're going to get what? Yeah. 0. What's e to the 0? The whole thing is 0. Okay. 1 minus 1 is 0. So in this case, that 49 actually does cancel out. This is the way it's working. Because of that 1 minus in front of it. If the 1 minus wasn't there. So, but that makes sense, right? They just jump. Their velocity at that initial point would be 0. All right. Find the velocity of the skydiver after 3 seconds. What is it? No, because you're jumping perpendicular to the plane. Velocity, the plane's going left to right, you're going to go down. So at that point, when you jump, your velocity would be 0 in that direction. Your velocity would be the speed of the plane in the other direction. So, well, yeah, until the wind acts on you. And a lot of these things are in like ideal type of situations. Again, like when you're looking at in terms of a realistic situation, it's not necessarily going to model perfectly. Yeah, exactly. Or the guy who was it? He jumped like 79 kilometers above the earth or something like that. It was like insane. Yeah, it was like the Red Bull guy who like literally had a spacesuit on and he jumped. All right, so what's the velocity after 3 seconds? $22.9. And then 5 seconds, 31.9. These are the two values that I got. So 3 and 5. This works well until you either go splat or you open your parachute. What's the formula for compound interest? Huh? Oh, per? Almost. That's continuously compounding. So, I think I actually have one of those. I didn't do that one. Continuously compounding is per. So, no, did I do that one? Nope, I did. Okay. So, compound interest is A equals P1 plus R over N to the NT. Continuous is P equals or A equals PERT. Perfect. Which is exactly the same formula that we just had for exponential growth. When you're compounding, N is the number of compounds. Annually. So in this case, we're compounding annually, so N is 1. If we were compounding monthly, N would be 12. Quarterly, N would be 4. Not necessarily. So N is when you're doing compound interest, it's typically always annually. However, this formula will work for technically anything. So if you're compounding daily over a month, you could actually do it at 30, like those things. It depends on what your interest is in. But for most, like I would 99% of all compound formulas, it's always based on annually. N is not always going to be 1, however. It could say compounded monthly, it could say compounded weekly, it could say compounded quarterly. So that N would change in those situations. This one is compounded annually, so it'll be 1. Or if it says compounded continuously, then we would use the E. So those are the two formulas you might need to know. So now you can figure out your student loans now. You borrowed $35,000. So that's P. 1 plus, my interest rate is 6.25%. You change it to a decimal. compounding 1. Unfortunately, your student loans compound daily. And then it's 1 times 14. And it says round to the nearest dollar, so $81,785. Now, if you go the nice direction, goes you invested $35,000, 14 years later you'd have $81,000. So which that would be nice. Not the other. And if this was compounding continuously, which it's not, but it would be 35,000 times e to the 0.0625 times 14. And you'd have $83,961. So a couple $1,000s more to continuously compounds. So while these problems might look complicated, there really is no calculus in it. The entire reason the section's in the book and actually go over it is to get you to understand that that exponential growth is actually a derivative by its definition. All right. When it says the rate of change y is proportional to y, that's exponential growth or decay, depending on which direction they're going. Okay. So this statement right there, that is just and all exponential decay would be is the exponent's negative. The k value that you find would be negative. If k is positive, it's growth. If k is negative, it's decay. So the process behind everything we've done is exactly the same. That never actually changes. All right, and they gave me 2 points. So use those 2 points to find your equation. All right, what do you get when you plug in 2? They want the exact answer. So this is why I told you not to round. So if you did ln of 100 over 40, which you should have gotten, you would have gotten 0.916. Da, 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 da. If you type that in, you round to say 2 decimal places, you get 251.86, and it keeps going. If you put 16 in, we get 249.8. If we put in the 2 and then the 9, we start getting closer and closer. But if you put in the exact ln of 100 over 40, you get 250. So, especially where it says use exact values in your answers, not decimal approximations, that's what that means. Don't round when you're doing these. Otherwise, sometimes you get a number that's not exactly right. So the answer to this one is 250. All right, last one. Okay, so it says a rumor starts among 10 students at a local high school with an enrollment of 510 students. The rumor begins to spread at a rate proportional to the number of students who have not yet heard it, with k equal 0.055 minutes to the negative first power. So that means it's 1 over that. Let y be the number of students in the school who have heard the rumor 2 minutes after it started. So we've got k. What is the equation for this? So how many students know about it right at the beginning? Okay, so y of 0 has got to be 10, right? Yeah. So we need to come up with our equation for it. So we know it's going to be some kind of initial value, but we're going to have some kind of an equation in here with e to the, we know what k is. K is 1 over 0.055 t. That's going to continue to grow, correct? So how would I set up my equation? 0.055. So if I did that, what's going to happen after? What happens after 1 minute? Huh? More students hear the. How many students have heard the rumor? If that's my equation, right? If we just did it the way we were doing the other ones, 10 times that, right? How many students have now heard the rumor? After 1 minute. Okay, so what is it? Give me a value, plug it in a calculator. Because part of this is figuring out where things are wrong. What'd you get? Like that?
Yeah, about that.
Okay. Does that make sense? No, it actually told me how many people are in the school. There's only 510 people. So that makes no sense, right? So when you're going through and doing the problem, sometimes you have to figure out, like, okay, what I did is wrong. This makes no sense. Now we have to go back and think about the question of where it's working at. Out of all the topics, this one's going to be the hardest because of that, the way that it's asking. Notice, it is not asking you for the E equation here. It's asking you for the differential equation. It's asking you for it before you actually do the calculation. Okay? So, when we look at this one, remember my initial problem when we first started this was just ky. What's k in this problem? So it's 0.055. Okay. How many students do I have in the school? Then it's going to be 510 minus that y. Because what we're looking for is we're looking for the change in students, right? How many less students now don't know about the room? So when it's looking for its differential equation, that's what it's looking for. It's not looking for the E yet. The next thing is asking about the E. Now that we have that as a differential equation, we can then change it into the actual equation that we need. So the 510 minus, and the y becomes what? How many students don't know about the rumor at the start point when I start doing the calculations? 500. E to the 0.055. That is totally misleading, the way they have that written. T. It's always going to be negative because the population's getting, the amount of students that actually don't know about it is getting smaller. So we're taking that away from that 510. So if this is 0, my initial answer is 10. Okay, so the question is do you understand how to get from the problem to that? Yep. So where does the 510 come from? Total amount of students. The 500 was how many students don't know about it at the beginning. Because in this case, it said there was 10 that knew about it. The K will always be the negative of whatever they have there. That's what that -1 is, which is totally misleading because that's a fraction, and that's not what they wanted. It was supposed to be negative there. So I have a problem with the way they worded this question. And then T.
Why is it negative?
Because it's the amount of students who don't know is decreasing. Yeah. Right. So it's like you're starting off, we have 510 students who don't know about the rumor, 500 students who don't know about the rumor, and that keeps going down. The amount of students who don't know about the rumor. So we take that, and then the last question just asks you to plug a number into it. So if we have 18, 10 minus 500 e to the 55t. So we have 324 students. There was a different version of the question that I'm looking at real quick for you. All right, so this is a different question, but it'll work for this one. So that's one way you can have the last question part of this question. The other way is this one, which asks this question slightly different. So this one, what is the rate of change of the number of students who have heard the rumor at the moment when 254 students have heard the rumor? So this sounds really confusing. However, there's one key word in it that actually makes this whole problem easier. Or key set of words. What is the rate of change? On this problem, what is the rate of change? Rate of change is what in calculus? The derivative, right? Rate of change is derivative. That's slope. Okay, so whenever we hear rate of change, it's slope, and that's the derivative. For this, that is my dy over dt. That's my derivative. So this bottom question is asking you to plug 254 into that initial problem that you have up there. So it's 0.055 times 510 minus 254. That's what it's asking for, not into the equation. That the on B. So if they're asking you how many students, you're plugging into the equation you found there. If they're asking you rate of change, you're plugging in into the derivative, which is the first thing you found. So make sure you read the question and figure out how they're asking, what they're asking for. All right, we have one more section to go over, which we'll do on Thursday. Then we will do the review. The review test should be already up on the books. I might tweak it though, because I've changed a few things since I wrote that test. But that'll be up there. I'll do that tomorrow. And then we'll review on Tuesday. Your test is next Thursday. Your test will be on paper, so you do not need your computers or anything else. Any questions?
Yeah, allow us to use decimals on that test.
Yes. And you can use your note card. Fight the authority.